So this is the sixth question of CodeChef Starter 119 Division 4, Unalike GCD and LCM. Okay. In this question, you're given an integer x and you're given few queries. Okay. And each query is of the format where you're being given a positive integer p, and we need to count the number of positive integers y such that GCD of x comma y power p equals to the LCM of x comma y. Okay.
Yeah.
Now, they have also mentioned in the question that the answer may be large. So, in case if it is larger, we printed modulus 10 power 9 plus 7.
Yeah.
Okay. And they have also mentioned that the number of y's are also finite. Since there is no upper bound to the value of y, it can be proven that for any p, the count of y's is always finite. Okay.
Yeah.
That is also mentioned. The constraint in this question, there are up to 10 power 3 test cases. X value can be up to 10 power 9. And for every test case, there are up to 200 queries. And the p value is also up to 10 power 9.
Yeah.
Okay. So in the sample test case, if you observe, the x value is 12 and the p value is 2. Okay.
Yeah.
So we have two possible for the first query, where the p value, here 2 is basically the number of queries. Okay. And this is the p value. Okay.
Yeah.
So for 12 as the x value and p as the q value, 2 as the p value, the only two possible y values are 18 and 144. And if you do these calculations, you will get to know that it will satisfy for these two conditions. Okay.
Yeah.
So yeah, that's how the sample gives that. So let's see how we can solve this question.
So basically, in this question, if we write down the equation, it is mentioned that GCD, we are given x and y. So considering that input parameters, we are given x. Considering that input parameter, y is something which we need to find how many y's exist.
Yeah.
So GCD of x comma y should be equal to power of p. GCD of x comma y with the power of p should be equal to x LCM of x comma y. Right. This is what is given.
Right. Yeah.
In the question, and p is given as a query. So x is always fixed, and we have queries where there is varying.
Yeah,
so considering p as some varying number, let's see if we reformulate this, what do we get? We know that we can write LCM as x into y by GCD of x comma y.
Yeah.
So this is our LHS and RHS. Let us send GCD to our LHS.
Okay.
Then it becomes GCD of x comma y whole power p plus 1 should be equal to x into y. Right?
Right.
So now from this, we can observe that y will be equal to GCD of x comma y power p plus 1 by x. Right?
Right. Yeah.
And from this, we can observe that whatever GCD we get, that should be divisible by x always. I mean, not GCD of x comma y, it is GCD of x comma y power p plus 1. That should be divisible by x.
Right. Yes.
Because y should always be an integer. So that, as that is mentioned.
Yeah.
So now let's see how we can solve this.
Right.
So this equation is sufficient enough to find out number of y's we need for any x and for any varying p.
Right.
So for that, let's define few things. Let us consider x has some prime factors.
Okay.
Let p1 be the first prime factor with a power of c1.
Okay.
p2 be the next prime factor with a power of c2. So on till pm be the next prime factor, pm be the last prime factor with the power of cm. Right?
Right. Yeah.
Now let us only consider one particular prime factor. Why? Because in the GCD, we for sure know there won't exist any prime factor which is not in this set.
Any prime factor
which is not in this set.
Okay. So yeah,
Why? Because we can see that GCD of any two numbers is nothing but in terms of prime powers. Let's say if we consider GCD of any two numbers x and y, and for now let's say in x there is a prime factor p.
Okay.
With a count of c1.
Okay.
And the same prime factor p1 with a count of c2. Let's call it as p only instead of p1. P is a common prime factor in x and y, or let's say it's not a common prime factor. Like in case if there is some prime factor which is not present, let's represent the c as 0 for it.
Okay, fine. Yeah.
So let's say p is one prime factor,
right,
and the power of p is c1 in x and
right,
c2 in y.
Okay.
Then we can always write it as then in GCD the power contribution of p would be minimum of
C1 and C2.
C1
right?
and C2, right?
Right, yeah, true.
So from this we can see for sure in the GCD there won't exist any prime factor which is not in this set, because if there is some prime factor which is not in this set, that means
that will not exist.
That will not exist.
Yeah,
so its
basically.
prime power is 0.
So basically in GCD of x comma y, all the prime factors in GCD of x comma y will be from this set only.
Yeah, will be from this set.
Yeah, that is true.
So now let us see for a single prime. So basically now let us break the problem into the following. We know that in y we can have some prime factor which is present in x, right?
Yeah.
Now let's find this out. That is, for a particular prime factor, we know that one more thing that we know is if there is some prime factor which is not present in x, then in y there will always exist one unique way only to have that prime factor as some power. Right?
Yeah.
So let's say here there is some prime which is p dash, let's say.
Okay.
In x, the power of this is 0, right?
Right. Okay.
And in y, p dash power is
some variable.
Let's say some variable v. Now, when we find out the GCD of this,
okay,
in the GCD, for sure we know p dash power would be 0.
Will become 0, right?
And if we just multiply the power with p plus 1, p is the given number. So it would be 0 into p plus 1,
yeah,
which is still a 0.
Right.
Now, 0. So now we should be able to divide 0 by 0. Not divide, we should be able to subtract. Right? So from the equation, if we see, in x, we have p dash power 0. Right?
Right, yeah.
And in the y also, we have p dash power 0. Right?
Yeah.
So now we know that y is equal to this thing. That means it is just subtracting.
You mean x has p dash power 0 and GCD of x comma y also has p dash comma 0.
No, p dash comma 0.
Yeah.
P dash comma 0 after multiplying the power inside, because p dash power is 0. So though we multiply p plus 1 to the power, it still remains 0.
Yeah, it still remains 0. Right.
So now we know p dash power 0 and p dash power 0 is present in x, is present in numerator and denominator.
Right.
Now we can see that there is only a unique way for y to have this power and to satisfy this RHS, right? That is nothing but we can just write here bases are same. So power is 0 in the numerator, and power is 0 in the denominator. That means we can write it as 0 minus 0, right? Because because it's a numerator and denominator, we'll cancel out the powers. We'll cancel out the numbers. That means we are subtracting the powers, right?
Right, basically, yeah.
So when we subtract it, the only unique value that we get is always a 0.
Yeah.
So for sure, for RHS to satisfy, in y, whatever prime is not present in x, that shouldn't be present in y also for RHS to satisfy.
Okay, so whatever prime is present in x should be present in y as well. Okay, so
whatever prime is not present in x shouldn't be present in y also.
Their powers can vary, but the prime factors should be the values of prime factors should be same, right?
Values of prime factors should be same.
Okay.
So here we actually prove, assuming p dash is not present in x. So from this we just saw that we could prove y in y also p dash should be
P
present.
dash will not be present.
Yeah.
Right.
Because from this,
Exactly.
if we analyze and formulate it,
right.
we found that the power should always be 0 for such a number.
Exactly.
Now let us. Now we just saw that we can just ignore all the powers which are not, all the primes which are not present in x, because all the primes which are not present in x has a power 0, and we just saw in y also their power will be 0.
Right.
So now let us fix a prime which is present. Right?
Okay.
And let us solve for that prime, and it holds for all the present primes.
Okay.
So let's say P1 is the prime which is present, and it has a power C1, right?
Okay.
In x. This is in x.
In x, right.
Now, in GCD of x comma y, all values that can appear for this power is, all powers that can appear for this prime is in the range 1 to C1 minus 1. Only.
1 to C1.
Okay, 1 to C1, not C1 minus 1.
Yeah, because C1 is also one possible.
C1 is also one possible.
Right, yeah.
Now, among this, let's split it into two parts. Firstly, 1 to C1 minus 1. Let us put it in one of the part.
Okay.
And C1, let's consider it separate.
Okay, fine.
These are the possible, in the GCD, these are the possible powers we can get for that time.
Yeah.
Now, firstly, let's solve for C1.
Okay.
So for C1, in my GCD, the claim is P1 power is C1. Right? That means, can I say, in X we know for sure the power of P1 is C1 always.
Yeah.
And in Y, for sure the power should be greater than or equal to C1, right? For this to hold.
Yeah.
C1. Now, but we don't know what exactly Y should have, because we still didn't simplify the RHS.
Right.
Now we know GCD is P1 power C1 whole power P plus 1, right?
P1 power C1 whole power P plus 1. Right.
And for now, let's ignore other prime factors. Only for this prime factor, this is what the contribution is.
Right.
Now, divided by P1 power C1. Right? So if we just consider this, in Y, what should be the power of the same prime factor? Can I say it should be C1 into P plus 1 minus C1? Okay?
Yeah.
So here if we see, there is always a unique.
So it will be simplified to C1 into P.
C1 into P. So always in Y, the power of this prime factor should be C1 into P. Okay? So we proved it for any prime and for any power and for any P value, right?
Yeah.
So for any such thing, if the GCD is perfectly C1, then always in Y there is only a unique.
Right. Yeah.
So that is why can we say that in case if we want our GCD to be C1, then the number of ways we can consider that particular prime in Y is only one. Right?
Yeah, there is only one thing.
There is only one.
That is true.
Now we proved that there is only one way for GCD as perfectly C1 to exist.
Okay.
Now let's consider GCD as 1, 2, so on till C1 minus 1.
C1 minus 1. Okay.
Now, in the GCD, power should be, okay, for now let's fix some number V.
Okay.
V ranges from 1 to C1 minus 1.
Some number from 1 to C1.
Some number from 1 to C1 minus 1.
Okay.
That is the power of prime P1
Prime P1, right.
in the numerator. That is in the GCD.
In the GCD, okay, fine.
Now, we know in X that number's power is always C1.
Yeah.
And we also know that C1 is always greater than V, because we are fixing only numbers from 1 to C1 minus 1.
Right.
Then the claim is, for sure, in Y, the power of V, I mean the power of the prime P1
P1.
should be perfectly V, right?
Should be perfectly V.
That is because we know P1's, like if we consider GCD, we just saw it is just minimum of both the power.
Right.
Then if X has C1 all the time,
Yeah.
and we are finding GCD of X and GCD of Y, and we want the GCD to be P power P1 power V. So it should be perfectly V.
Right.
If it need to be perfectly V, then it should be perfectly V in Y.
Perfectly V in Y also.
Then only it exists. So now we'll just check if this is a valid V or not.
Okay.
So for the V to be valid, we can see that in P1 power V. This is the numerator part.
Okay.
We are assuming that we can make a GCD P1 power V. Like
Right.
in the GCD, we can get a prime power contribution as P1 power V.
Right. We fix the V value.
Yeah, we fix the V value.
Okay.
And for this, P plus 1 will always exist.
P plus 1
By
divided by P1 power C1.
C1. Right? So for this V to be a valid V, which satisfies the above condition, which is Y is equal to GCD of X comma Y by X
Right.
power P plus 1.
Also, this will result to a P1 power V only, right?
Yeah. This one
Because-
results to a P1 power.
Because Y should have P1 power V.
Yeah. So now when we simplify it, it means V into P plus 1 minus C1. This should be equal to V.
V only, right? Yeah.
Then only we can say this particular V is a possible GCD. So we can count how many such values exist in the range 1 to C1 minus 1.
Yeah.
And we can also observe that only one
So
such value
we
exists.
need to find how many values of V exist from 1 to C1 minus 1 such that V into P plus 1 minus C1 equals to V.
Yeah, equals to V.
Okay.
And one more claim is only one such value can exist.
Okay, only one such.
Why? Because this is always an increasing function.
Right.
It
Yeah.
will never be constant.
Okay. Okay.
So that is why, like, let's say once we found some V which satisfies this condition,
Yeah.
then if we increase the V, it will never satisfy.
If we increase the V, it will never satisfy because we are increasing the left hand side.
Yeah, we are increasing this, but this is always constant.
Okay. Right. Yeah, that is good.
So
If P, okay, P is always minimum 1, right?
yeah, P is
So-
always minimum.
If P was 0, then it would not be possible at all.
Yeah, it wouldn't have been possible.
But okay, fine. Yeah.
But
They
yeah.
mentioned in the question P is starting from 1.
Starting from
So that will not apply.
that will not. So only one such value can exist.
Okay.
But though this observation isn't made, it's sufficient to solve.
Okay.
We can just iterate a loop and then find out how many V values satisfy it. Because we can observe that C1 will always be very less. C1 can at max be 30, less than 30.
Right.
Because a prime's power can be till 30 only.
Right. Because
Excess
the lowest
10
prime is 2, and
Yeah.
even 2 power 30 will become
More than-
around 10 power 9 or
Yeah,
something.
around
Right?
10 power.
So any other prime will never go above 30. Right. Okay. Yeah.
So for
So
every
can we be sure that there will always exist such a P value, such a V value that will satisfy this condition?
that we can't be sure.
Okay, that's why we run a loop from 1 to C1
C1.
and 1 to C1 minus 1,
Yeah.
and we check for all the cases.
Yeah, we check for all. Or instead of running a loop, we can reformulate this also. It is like V into, if we just reformulate, our aim is to satisfy this condition. Right?
Yeah.
We should check if there exists at least one V value.
Right.
If there exists V value which satisfies this condition. So V into P plus 1 minus V should be equal to C1.
Yeah.
So V into P should be equal to C1. This is what should go.
Right.
So now we can observe that for this to satisfy,
It should be C1 by P.
that means C1 should be divisible by P.
Okay. Then.
So we can, so from this simplified equation, we can just check if every prime power, basically if, firstly, let's compute all the prime factors of x
Right.
and check if every prime power, that is, let's say prime factors are p1 power c1, p2 power c2, so on till pm power cm
Right.
of x. Then we can just check if c1 is divisible by p or no, right, from this condition.
Yeah.
If it is divisible, then there will exist one such thing. So for such things, we should multiply 2.
Okay.
And for all other things which, in which this is not true, that is C1 won't be divisible by 2, we should multiply 1, because there will only exist one value, that is perfectly C1. Because we proved C1, if we fix GCD to the C1,
Okay.
then it is always possible.
Yeah. Got it.
It is always possible, and there will only exist one such power value in Y
Right.
for that particular base point.
Right.
So now let's discuss the time complexity, considering we are fixing, we are basically just checking if the prime power is divisible by p or not.
So for every prime power, every prime factor's power, we just check if it is divisible by p or not.
Yeah.
And those many possibilities will exist, right?
Those many possibilities will exist.
Okay.
Because here we can see every prime factor is individual, right?
Right.
So until p power cm.
Okay.
So for p1 power c1, we found in y how many choices do we have? Like how many choices of p1 power something we can put in.
Okay.
So, and we saw that the choices can be only two, one or two.
Right.
So that is if c1 percentage p, if that is 0, basically if c1 is divisible by p, there are two choices. Else there is one choice.
Okay. Two choices because one is
One
C1,
is
one is
C1,
C1 itself,
C1
and the other one is
some
any
value.
some value between them,
Yeah,
right?
between.
And in the other scenario, there is only C1.
And that value is nothing but c1 divided by 2.
C1 divided by.
So because we want an integer only, so c1 should be divisible by 2. Then only that value exists.
Right. Exactly.
Which we just saw it from this.
Right. That is true.
So that is why from this we could prove that there can only exist two choices, either 2 or 1.
Can we take the sample case and just quickly say?
Okay.
So x value is 12.
12.
And number of queries are 2.
Okay.
And in query we have one p is 2 and one p is 3.
So firstly, let's take P2.
Okay.
So now for 12, the prime factors are 2 power 2
Power 2.
and 3 power 1, right?
Power 1. Right.
So now let's see for 2, how many choices do we have? 2 power 2, here the power value is 2 and the p value is 2, right? Yeah. For the query. So this is divisible.
Yeah.
That means in y, if we want exact prime contribution in y, then in y we can either put 2 power 2, right? Or okay, not 2 power 2. It is, if we consider c1, then it would be 2 into 3.
Okay.
Minus 2 into 3 minus 2, right?
Yeah.
Which is 3. So we can either put no, it's not, it's 4, right?
Yeah.
So we can either put 2 power 4 by 2 power 4 in the sense the first case. First case is when we consider c1 itself.
Okay.
Then what is the value which we derived, right? This will always be the value, which is c1 into p.
C1 into p.
So c1 into p is 4 here. So it can either be 2 power 4 or it could be 2 power 1, right? That is because here if we see c1 is 2 and p is also 2, they are divisible.
Right.
And one possible v value is c1 by p, right, which is 1. So 2 power. These are the two possible choices. And for 3, the choices are, we can only put 3 power 2.
3 power 2. Right.
That is if we directly consider c1. But there is no one more choice. Why? Because here 1 is not divisible.
Right.
So 2 and 1. So in total number of choices are multiplying these 2 and 2.
Right.
So for this test case, answer is 2. That is one. And for 12, the prime factors are
because we just multiply and you
No.
2 into 1. Right?
2 into 1.
Okay. Got it.
So 2 power 2 into 2 power 2 and 3 power 1 are the prime factors of this.
Yeah.
And the next query is p is equal to 3. So in this scenario, for this, there will only exist one value.
Yeah.
That is, if we consider c1 itself as the
so,
as the power contribution of that frame in the GCD.
Right. So 2 power 4.
It would be 2 power 4, which is no, it would be 2 power 6 because it's c into p, right?
Okay.
The derived value of c. And we won't get one more value because 2 is not divisible by 3.
Right.
Similarly, for 3, the value is 3 power 3. Right? We won't get other value, which is as 1 is not divisible.
What does this 2 power 6 represent?
2 power 6 represents the power contribution that y can have. The 2 power contribution that y can have.
The power contribution that y can have.
So in y, only 2 power 6 can be present.
Right.
For the power contribution of 2. And only 3 power 3 can be present as the power contribution of 2. Similarly, in the previous case, in y, 2 power 4 could be present in the y as 2's power contribution.
Okay.
And 2 power 1 can be present in y as 2 power as the 2 powers value.
Right.
So this is for what all 2 power forms can y have,
right,
and what all 3 power forms can y have.
Yeah.
Similarly, here it is what all 2 power forms can y have, what all 3 power forms can y have for a particular p. P is like the given query pattern.
Yeah, that is true.
So here there is one choice and one choice. In total, there is only one choice. So now if we look at the time complexity of this, then firstly for x, we are finding out the prime factors.
Right.
So we can say prime factorization costs us square root of x in the worst case.
Yeah.
Into, for every query, we are just iterating over its prime factors. And we can say number of prime factors could be, or I'll just represent it with length of the prime factors.
Okay.
Prime factors of x, right?
Okay.
This represents prime factors of x. Yeah. And this won't be more than 10 approx.
More than 10. Okay.
Or not 10, we can say 12 maybe, not more than 12.
Right.
To analyze this, just multiply the first 12
prime
factors.
That value will
be more than 10.
10 right?
So that is why it can't be more than. So from this, we can say that time complexity is big of square root of x into q into prime factors of x. This is per test.
Per test. Right.
And space complexities, and this is sufficient enough as test cases are just 1000 and x can be till 10 power 9 in the worst case.
Yeah.
So in the worst case, we can just analyze that it would be 1000 into approx square root of, and it's not into q. This should be plus q into length. Because for every query we iterate over prime factors of x.
Right.
And this is computed separately, not for every query.
Yeah, that should.
Before the queries, we pre-compute all prime factors. So it is square root x plus q into length of prime factors of x. And we can see that square root x is very large compared to this value, as
Yeah.
queries can be 200 and length of primes can be 20 at max, can be 12 at max. So in the worst case, we can say it would be 1000 into square root of 10 power 9, which is nothing but 1000 into, we can say 3 into 10 power.
Yeah.
So which is sufficient enough to pass in 1 second.
Right.
And if you see the space complexity, we can say for this, the space is constant only. We can say it's big of 1 only, as prime factors won't be too many. It can at max be 12.
Yeah.
So we can just conclude that as big of 1.
Yeah. Basically, we don't have to store anything for every query we compute and we keep processing.
Yeah, we keep processing. And space complex and time complexity, if we implement considering considering the simplified part, that is just checking if C1 is divisible by 3.
Okay.
Then the time complexity would be square root of x plus q into length of prime factors of x.
Right.
But the given constraints even allow us to brute force and then check if there exists any b on.
Okay.
That is, fix every value from 1 to C1 and then find if there exists a b on.
Right.
Even that is allowed.
Okay.
So it depends on how you implement. If we implement in that way, we'll get one more factor of into 30 at max, not more than 30.
Okay.
And we just discussed why this is 30 in the verse, because 2 power can be 30 in the verse. And we can say both of them combined will result in 30 into, let's say, the factor that we are multiplying is c, and c can be 30. Both of them combined will be 30. This one into this. Why? Because in case if there is a prime factor 2 with a power of 30, then for sure there can't exist any other prime factors. So more the power we increase for a prime factor, lesser prime factors will be present later. That's what we can obtain. So we can say, as an approximation, both of them together will be near to 30 to 40 approximately. So even that is still sufficient enough to pass in the given.
Yeah, I think
so this way we can solve it.